And now it's my pleasure to welcome a speaker who will join us remotely, Stefan Wasilewski, who is coming to us from Luzern. He's at the Hochschule Luzern, where he's a research associate and doctoral candidate, and he also is part of EPFL in Lausanne. And Stefan's research focuses on strategies for efficiently finding the most significant details that characterize the full distribution of daylight conditions within a space. He's an architect and a consultant, and I hope we will have Stefan with us on screen momentarily. Stefan, welcome. Nice to see you.
Hi, thanks for having me. Hi.
We're going to let you take the floor, and thank you for talking about daylight simulation beyond a grid of points. It sounds very exciting. Thank you, Stefan.
Well, we'll see about that. I guess I'll just wait for my slides to get up here. There we go. Okay. So hi, and thanks in advance for listening to my presentation. Today I'm going to talk about the importance of representativeness for characterizing the daylight in an architectural space, as well as a simulation method that helps to efficiently reach this goal. Here, representativeness describes how similarly a set of samples behaves compared to the totality of conditions that occupants in a future building will experience. We experience the world as a continuous space that we move through with the passage of time. But when we simulate a representation of our experience of daylight in buildings, we instead deal with discrete instants. Discrete rays from a point are intended to estimate the continuous distribution of light at a point. Discrete points in a space estimate the continuous distribution of light in a space. And these rays are evaluated for a set of instantaneous sky conditions meant to represent some continuous passage of time. The resolution of these samples needs to be high enough to represent the salient features, but maintaining this level of detail across all these dimensions is computationally prohibitive. So how do we best allocate a budget of rays determined by practical limits? The method we have developed uses an iteratively guided sampling approach based on the structure of a discrete wavelet transformation. If that all sounds very technical, I'm not really going to talk about it too much during this presentation, so don't worry about it. This effectively identifies significant variance across a wide range of frequencies, which are used as a probability distribution to select additional samples. In the image series on the right, beginning in the upper left, a low-resolution sampling is used to estimate the importance of possible additional sample directions based on low-frequency variance. Additional samples drawn from this distribution refine the estimate. The process iterates, successively reducing the variance between samples at higher and higher frequencies until a final target resolution is reached. On the left is the uninterpolated false color image reconstruction generated from these sampling results. In addition to directional sampling, this strategy is also effective for sampling source directions and positions within a space. This yields high effective sampling resolutions across all these dimensions with low overall sampling densities, leading to an efficient way to simulate a representative set of conditions. Where the distribution of conditions is changing rapidly, the distance between samples is smaller. And when the distribution is more uniform, the sample spacing can be larger. In other words, in low variance regions, a single sample is taken as representative of many nearby samples. So the main question I'm exploring today is, why do we need this effectively high resolution data? Prospective daylight simulation, or simulating something that does not yet exist, as opposed to validations or other comparisons with measured data, makes up the vast majority of analyses done in practice. These include comparative performance analyses, compliance modeling, and descriptive simulations. In many of these cases, the question boils down to how a particular intervention impacts the daylight in a space. To assess this impact, a useful framing of the question is, how much of the time does how much of the space have daylight condition X? To answer, our results either need to be sufficiently representative, in which case we can directly quantify the answer, or we need to be able to generalize to make some conclusion. Given this example of a deep room with windows only on the south elevation, we can imagine generalizing from the plans on the right to the single section on the left. While the section will vary across the space from east to west, it will do so fairly uniformly between the three options shown here. Looking at the section, we can also see that a single point deeper in the space could just as effectively characterize these options, as the relative difference between the options beyond 5 meters is fairly constant. Knowing the transmission properties of these facades, we can even be fairly confident that the relative difference at a single point between these options will remain fairly constant across almost any sky condition. But what happens if the room shapes are different, or the windows are different sizes, or on different orientations, or we assume the blinds and shades are dynamic, or if we assume there are different control algorithms for the shades and blinds? In these cases, we cannot generalize from one time step to all the others, or from one point, or even from one section. Only by fully characterizing the spatial and temporal domain can we hope to understand the trade-offs between interventions. But even if we simulate everywhere and every time, how do we know that our simulation matches the proposed future reality? In a 2016 article titled "Uncertainty in Daylight Calculations," Tregenza begins, "There is uncertainty in every daylighting calculation, an inherent and unavoidable imprecision which exists in addition to any error due to inaccuracy in a numerical model. It occurs because neither the future state of a building nor the future luminance pattern of the sky can be predicted with certainty." So one potential response to this, which is the one suggested by Tregenza, is to quantify this uncertainty and appropriately convey it with the results. On the left, I show a 20% error in the simulation modeling as a high-end estimate of the error found in a number of radiance-based simulation validations. On the right, the error bands show an estimate of the range of plausible illuminance values at this point in time based on likely weather conditions. Compared to the 20% simulation error, and even the 100% relative difference between window treatments, the weather uncertainty between the lowest and highest plausible condition is between a factor of 10 and 30. So this amount of uncertainty is potentially quite demoralizing. What can we possibly gain from a 10% improvement in simulation accuracy if we can't estimate anything within a factor of 10 anyways? Should we just use this to justify falling back to simpler heuristics? Can we even say anything useful about the difference between blinds and shades? Some component of the simulation error will have to be taken as true uncertainty, but the rest, as well as the range of possible weather conditions or dirt on the windows or any other changes, has high covariance across the comparisons. In other words, weather uncertainty, as long as we have a representative set of sky conditions, will not flip the order of the results. Each option will move in tandem across the error band. By viewing the error band as a range of possibilities with differing probabilities rather than uncertainty, we can actually have more confidence in a simulation based on a single state. If the distribution of these conditions is similar to the distribution of future weather conditions, by solving for this range of possibilities, we have a more representative sample. While this might sound like it leads to even more simulation, climate-based daylight modeling using hourly, daily weather data already effectively does this. Nearby days with similar sun positions capture a distribution of sky conditions that aims to be representative for the season. It is just important to note that within this range of conditions, the association between exact sun position and sky condition is relatively meaningless. Unfortunately, the false precision of common results formatting and presentation disguises this fact. So how representative are the sky conditions we typically use? The representativeness of the sky is determined by two things: the selection procedure for the sky conditions and the model used to translate the measured values into a sky distribution. Regarding the first, here is data from two TMY sets for the same site and similar collection periods. The only difference is the standard used to select the typical values. The difference between these two distributions is explained by the different weightings applied to all the weather measurements used to determine what is typical. These measurements include values like temperature and wind that do not directly impact light. We don't actually know which of these weightings is better at generating realistic distributions of interior lighting conditions, but the TMY3 method does more heavily weight the key parameters for daylight. Unfortunately, this data set is only available for the United States, and in the case of comparisons of performance across site, such as performance standard simulations, a consistent selection procedure is probably more important than individually being more like reality. So there are trade-offs either way. Regarding the model, the commonly used Perez all-weather sky model is often taken as an instantaneous distribution, which in the case of the sun location, it is. But the brightness of a particular sky region is really a prediction of the average condition for all skies with the same input parameters: sun position, direct normal irradiance, diffuse horizontal irradiance, and the dew point temperature. For cases where most of the sky is visible and what matters is the integral, This distinction does not matter as much as when the brightness of a particular sky region has outsized importance, such as the direct view from a window, or what we deal with daylight in buildings. In spite of these limitations and uncertainties, the combination of sky and weather selection models are still useful for climate-based daylight modeling, not because they predict the future, but because in many cases, this distribution of conditions will respond to interventions in a similar fashion as reality. So now moving back inside the building, this plot shows a single viewpoint and direction characterized by the relative brightness measured by the log of the vertical illuminance on the y-axis, and contrast as the log of a contrast term related to those used in glare metrics like DGP and UGP, except without any total energy dependence throughout a typical meteorological year. For this distribution to be meaningful, it needs to be representative of the likely experience of the future building occupants. In addition to using a physically plausible rendering algorithm and sky conditions as already discussed, the distribution of evaluated positions and directions must also be representative. This can either be achieved by sampling from these underlying distributions or by knowing the proper weight of each sample. The daylight coefficient techniques underlying most climate-based daylight modeling workflows are effectively a uniform survey of possible sky conditions and sun positions. The application of a sky matrix reweights this to be more representative of the site. This ends up being an extremely efficient way to speed up simulation, eliminating the repetitive calculations that would result from sampling complete sky distributions according to a directly representative distribution, and ensures sufficient sampling of even infrequently occurring sun positions or sky covers. To illustrate this histogram shows the level of reuse for the direct sun calculation. Each simulated source or sky patch is used for a certain number of hours, the x-axis, and the y-axis shows how many such simulated sources are in each bin. The two series show different intervals of data. Note that a shorter interval in yellow is more representative of a continuous distribution and uses the source patches more evenly, where the hourly data, a large number of hours can rely on a single calculation. Over 80 hours, or roughly 2% of the total results in the case of the most extreme condition seen here, which is a possible source of bias in our calculations. For hourly data, there are about 200 patches representing around 4,100 hourly sun positions. For the 5-minute data, 250 patches represent around 2 million sun positions. The extra burden on simulation here is small, only 250 divided by 200. And in fact, since many implementations do not pre-filter the sun positions, there is effectively no simulation cost. But 2 million time steps would be a significant burden for the post-simulation calculations. Of course, if we are using hourly weather data for the sky conditions and approximating sun positions, these 2 million conditions don't actually contain additional information. They just ensure that the distribution of source positions is more representative of the actual solar transit. Borrowing from the principles of Monte Carlo integration fundamental to the underlying rendering algorithms we use, adding some randomness to the way we select the precise time steps to evaluate will be just as effective. To illustrate this, here are two subsamplings of the continuous annual solar transit. The left shows a stratified subsample of all of the hourly sun positions, and on the right, a uniform stratified subsample of the continuous solar transit. With roughly the same number of source positions, the uniform sampling is clearly more representative of how the sun actually transits the sky. The last component of representativeness is the choice of metrics used as a means of understanding something about the occupant's experience. Returning to the brightness and contrast distribution from a point within the building, this plot is only possible to generate with image-based or directional data. These two plots are for identical views in the same office layouts, but one is facing east and one facing south. The distribution along the brightness axis is similar, but the contrast axis reveals the difference in experience. An illuminance-only calculation would not capture this. The concentration of conditions within a narrow contrast band is typical for a single view location, and is why illuminance-only glare proxies are often considered accurate enough. But the presence of low-angle direct sun and specular reflection, which are the source of the high contrast cases for the east office, is the defining characteristic separating these orientations. And I don't think anyone would argue that orientation and latitude are not important for understanding daylight. Returning to the east-facing office only, the plot on the left is generated from high-resolution, single time-step renderings for annual hourly data. It represents as close to a ground truth of the modeled condition as is realistically attainable. But it is not practical for prospective simulations in practice, because it took several weeks running on a large server to generate the data for a single viewpoint. We use this reference data set for this view and 7 others across different daylight conditions in a building to test the accuracy of the ray traverse methods. Much like how point-in-time sources are representative of a continuous temporal dimension, each ray sample, each analysis point, or each pixel in an image is a discrete measurement representative of a continuous spatial domain. The accuracy of this approximation, as the distance from the representative ray increases, depends on how quickly the scene is changing. The ray traverse sampling methods space samples according to this variance. Working in tandem with sky and sun coefficient methods, a much smaller set of samples can be used to reconstruct a nearly identical distribution of conditions to a set of high-resolution point-in-time simulations. Like any simulation workflow, the accuracy is not a fixed target and will heavily depend on the rendering parameters chosen. The distribution of results shown here is from the fastest set of parameters that provided reliable results across all views. To offer a point of comparison for the efficiency of ray traverse, we also tested a comparable existing climate-based daylight modeling methodology. Given our scene conditions, clear glazing with no automated controls, and our target glare metrics that require high source resolutions, we chose an image-based 2-phase dynamic daylight simulation method. Sometimes it's also known as the DaySim approach, but with a higher direct source positional resolution. At high image resolution and high accuracy rendering parameters, the 2-phase method can also match the distribution generated by the reference method. But tuning the parameters to generate results in a comparable time to the ray traverse simulation reveals that a uniform sampling approach breaks down, and it becomes impossible to reproduce the defining characteristics of the temporal daylight distribution. Using a pairwise comparison to directly measure the accuracy of each hypothetical time step shows that across a full range of parameters, from high quality to low, ray traverse, the orange lines, is, for any given simulation time, more accurate than the comparison in magenta. The y-axes of these graphs from left to right show the mean absolute error and sign deviation for UGP, DGP, and the relative error and sign deviation for vertical illuminance. The x-axis shows time on a log scale, given as hours per point per processor, where a point includes the full sphere of incident light. On the laptop these tests were conducted, which has 12 processors. This means that the fastest simulations took less than 5 minutes per viewpoint for hourly annual results. Each data point in the plot represents the mean of all 34,000 pairwise deviations from the reference simulation for a single parameter set of runs. What this shows, especially for UGP and DGP, is that we were not able to find parameters for the 2-phase method that produced unbiased results in less than 6 hours per point per processor, whereas an equivalent accuracy using ray traverse only took about 50 minutes. Ray traverse also performs better for illuminance, but not without some increase in error and bias. The relative deviation for vertical illuminance steadily increases at lower times, but is still less than 5% in the 50-minute runs. This is mostly driven by low absolute illuminance conditions, which explains why this error does not visibly appear for DGP, which is heavily dependent on illuminance. In fact, this pattern of higher error at lower illuminance is to be expected in the ray traverse method. As ray sampling is driven by variance, small absolute deviations, which will matter for low illuminance scenes, are not targeted for additional sampling. The accurate and efficient characterization of the spatial and temporal distribution of daylight is a powerful tool that can now reliably answer the question, how much of the time does how much of the space have daylight condition X? It will depend on human occupant studies to continue to explore which characterizations of daylight conditions are most representative of lived experience. But we now have the simulation methods necessary to accurately capture the distribution of these experiences, which means we can directly quantify how design changes modify this experience. Unlike simplified proxy measurements or simulation methods which rely on bounded assumptions about materials, mechanisms, and behavior, my hope is that a more representative characterization of daylight could even teach us something new about how we can utilize daylight in buildings. So thank you for listening, and I would also like to thank my collaborators and advisors from Hochschule Luzern and EPFL. There's more information about using RayTraverse, which is completely free and open source, and that can be found at raytraverse.readthedocs.io. And if you're curious, you can also find a short presentation describing how the directional sampling works in a bit more detail. Just look for the link under tutorials. So yeah, thanks, and that's the end of my presentation.